Assalamualaikum and good day everyone. Welcome back. In this video, I would like to give lecture about finite element method. We just consider 1D, 1D finite element. Okay, we start with displacement. In finite element, we need to start with displacement first. Let's consider this element. I and J represent the node and the coordinate. At node I is x equal to xi, and at J node we have x equal to xj. This is just a position of node. So after displacement take place, so this will go to ui, okay, ui, and ui is a function of u x, the position x I. U is a position of u xi. So this node will go to new displacement. Okay, so this is uj. So uj is a function of u at position xj. And we have x here. So x is here, maybe x is the origin is here. So at any point here, okay, any point, so the position is x. So the position is x. So this point will displace to u of x. So after displacement take place, so the element will go to here. Okay, so this is displacement. This is displacement. So after displace take place, so this is after displacement take place. So this point go to ui, and this point go to uj. The problem is, what is ux? Okay, ux. So in finite element, ux we need to approximate by using a polynomial. So the general polynomial is this: ux is equal to alpha null, alpha 0 plus alpha 1 x plus alpha 2 x square plus alpha 3 x cube, and so on. So all this we call a polynomial. For 1D element with two nodes, this is two noded element, we ignore. Okay, we just consider alpha 0 plus alpha 1x, and we ignore the rest. Okay, we ignore. So we just consider alpha 0 plus alpha 1 x, where alpha 0 and alpha 1 represent the constant. So in the finite element, we need to find alpha 0 and alpha 1 first. We have two parameters here, alpha 0 and alpha 1. So how to find alpha 0 and alpha 1? We need two, two boundary condition. Okay, the first boundary condition is at point I, where we know the position x equal to xi, and at point j or node j, we have x equal to sj. So we know, so from here, we need to take this boundary condition. Okay, so at x equal to xi, okay, x equal to xi at point I here, x equal to xi. So we substitute to this. So u xi now. So u xi, function of xi, equal to ui, and this is equal to alpha 0, okay, comes from this term, alpha 0 plus alpha 1 x now equal to xi. So this is equation 1. Okay, the second boundary condition at node j, x equal to xj. Okay, so we substitute x equal to xj here. So u x equal to xj, yeah. So now x equal to xj. So u at xj equal to uj. So this is equal to alpha 0 plus alpha 1, alpha 1. So now x is equal to xj. So this will form equation 2. Okay, from here, that's why we just need two term of this polynomial, alpha 0 plus alpha 1x. We ignore the rest term. Why? Because we have two parameters here, alpha 0 and alpha 1, and we need two boundary condition or two equation. So first equation comes from first node, and second equation comes from second node. So if we have, for example, 3 nodes, so we need to consider one more term, alpha 0 plus alpha 1x plus alpha 2x squared. So if we have 3 nodes, but this case, we just consider 2 node element. So from equation 1 and equation 2, we can form vector or matrix multiplication. So this is comes from this ui. So this is ui. So this is ui equal to alpha 0. So 1 times alpha 0. So this term plus xi times alpha 1. So comes from this term xi multiplied to alpha 1. And second term here, uj, so comes from this term or second equation. So alpha 0, so 1 time alpha 0 is alpha 0 plus alpha 1 sj, so sj plus times alpha 1. So this is come from this term. So we have developed the matrix equation. We need to solve now alpha 0 and alpha 1. We need to solve alpha 0 and alpha 1. So once we solve, we multiply first. Okay, we multiply all left and right of this equation. 2, 1 x I 1 xj inverse. So we multiply both left and right hand side by this term. 1 xi, 1 xj, the matrix, and we take inverse. So the left hand side, if we multiply to this, so we get this. Okay, so this is from left hand side. We multiply first to this, and from right hand side, okay, this term, if we multiply to this, so this inverse time this matrix, the matrix is the same, this is inverse and this is non-inverse. So if we multiply to this, we will get an identity matrix. Okay, an identity matrix, and this is alpha, we multiply one more to alpha 0 and alpha 1. So this is here. Okay, so this is I times any matrix A, or I times any matrix A, we will get A. So we can cancel this. So we can find alpha 0 and alpha 1 by this. Okay, so this is first step in finite element. We need to solve the parameter alpha 0 and alpha 1. Okay, I need to take a screenshot before we go to next slide. Okay, from next slide, we are going to solve alpha 0 and alpha 1. Okay, so we need to find inverse first. So this is formula of inverse. The formula of inverse A, B, C, D is equal to 1 per AD minus BC. And the matrix, this DA, we change the position. DA, we change position. BC, we does not change the position, but we just take or put the minus sign. So minus B here and minus C. So this is formula from your the formula of inverse of the matrix 2 times 2. You learn this in the secondary school. So come back to this equation. Okay, so alpha 0 and alpha 1 now equal to inverse this. Okay, inverse of this matrix just now. Multiplied to UI uj. So we use this formula, the inverse formula, to find this matrix inverse. So we will get 1 per 1 time Sj. So this is Sj minus Xi times 1. So we get this. So this we get from this AD minus BC just now. And this matrix, we need to change the position 1 and xj. So now we have changed the position xj and 1. This not need change position. Still maintain xi and 1, but we just put minus sign here. Okay, minus and minus. So once we solve this or multiply, we will get this. Okay, so we will get this. So now this is alpha 0, alpha 1. So from here we found alpha 0 is equal to this and alpha 1 equal to this. So alpha 0 is the function is in terms of ui and uj. So ui and uj all are nodal displacement, and sj and si are the position of node. So sj minus si, this is also position of node. So sj minus si is equal to L. L is length of the element. So this is element just now. This is node I, and then this is node j. So this is position is si. This is position is sj. So sj minus si represent the length of the element. So this is L. Similarly for alpha 1, so we found that this is a function of nodal displacement ui and uj. So this is also length of the element. Okay, once we found alpha 0 and alpha 1, so we need to substitute alpha 0 here and alpha 1 to the first equation just now. So this is first equation just now. This is first equation. So the alpha null and alpha 1 in terms of ui and uj just now. So we need to substitute here. Okay, so this is equation 1. Okay, once we need to substitute, this is alpha 0, we need to substitute to this alpha 0, and this is alpha 1, so we need to substitute to this. Okay, so now we go to next slide. After okay, alpha 0 and alpha 1 can be simplified here from last slide. So this is alpha 0 equal to this, alpha 1 equal to this. So we substitute from this alpha 0 and alpha 1 to the equation 1. So this we alpha 0 we found just now, we substitute to this, and this we substitute to alpha 1 here. So now this is ux equal to, so this is alpha 0, okay, comes from this, plus alpha 1. So alpha 1, this is alpha 1, comes from this, multiply x. So multiply x. And then go to simplify. So we found, and we factor all term ui and uj here. So this is ui and uj. This is factor. This is factor. So this multiplied to ui comes from this. Okay, so multiplied to ui. And the second term in this matrix multiplied to uj. So we take from this. So this vector multiplied to uj. So this vector multiplied to uj. So we found now ux now. This is ux. So this element, this is ui, uj. Okay, ui, uj. This is ui, and this is uj. So after this place take place, so this is new deform shape of the element. And the position here is xi, and this is xj. So this is ux. Okay, so this is ux. Position here is x. So this is from this point go to, or this place to this point. So the displacement is ux. So ux here, u is the displacement at a position x is a function of x. So ux here, this is ux, and ux now we can predict by this term. Ux now is a function of nodal displacement ui. So this is ui, and the function of uj. This is also a nodal displacement uj here. So the rest is function of nodal node position. So sj, si, sj, si, si, and sj all are nodal position. So si and sj. So ux is a function of x. So of course this is a function of x. So displacement here, ux is a function of position x. Okay, so we can conclude here, ux is a function of x position and nodal position si and sj, and nodal displacement ui and uj. So go to next slide. This ux okay, this term, this is comes from previous or last slide. So this term we call ni, and this term we call nj. This is nj. So ni and nj are shape function. So ni is shape function at node I. So we call ni is a shape function at node I. And nj is a shape function at node j. So we introduce an I and an j here. All are shape function. We call it as shape function, where an I is this, comes from this, and nj is this, so comes from this. Because this is an I and this is an I and this is an J. Yeah, or we can also we can from this we can also simplify that ux is ux from here is an I. So this is an I here, an I function of x plus nj. So this is nj. So this is an I of x, and this is nj of x. So this is nj of x multiplied to uj. So from here, we can say that the displacement at any point in the element ux is equal to a shape function nix times ui. This is nodal displacement at I node plus njx. This is shape function at node j, where this is also a function of x, and multiplied to uj, the displacement, the nodal displacement at j. Okay, so from here we can simplify that ux equal to, so this term we call n. Okay, and then this term, this is nodal displacement, we call u. So ux is equal to n, so this is a row vector. This is a row vector n, and uj, this is a column vector. Okay, we introduce the column vector here. So this is a row vector. We call it as a row vector. So this is this term we introduce as a nodal displacement u times u. So ux equal to n u. So if we have three nodes. Okay, just now we just consider this element has two nodes. So same happen if we consider the element has three nodes. We can use same procedure just now. So if we have three nodes, this is node I, this is node J, and this is node K. First, we need to approximate the displacement first. So this is go to UI, displaced. So this is displaced to UJ, and this is displaced to UK. Yeah? So this is UI, UJ, UK. The coordinate is SI, the position is SI, XJ, and this is XK. At somewhere here, we have a point. We have a point. So this will displace to the point here is the position here is x. So it displays u function of x, u of x. So we need to consider again this. In a finite element, we start ux, the displacement function, u function of x, is predicted by using a polynomial. So this is alpha 0 plus alpha 1 x plus alpha 2 x squared. Okay, alpha 0, we need two parameter or two constant, alpha 0, alpha 1, and alpha 2. So three constant because we have three node now. So the boundary condition is x u. The boundary condition is u at xi equal to alpha 0 plus alpha 1 x I plus alpha 2 x I square. We continue to here. Okay, we continue to here. So the second boundary condition. Okay, so u at xj equal to, we use this, alpha 0 plus alpha 1 xj plus alpha 2 xj square. So we found second equation. So next equation is comes from this boundary condition. This is uk. So u xk or uk equal to alpha 0 plus alpha 1 xk plus alpha 2 xk square. So this is equation 1. Okay, equation 1, and this is equation 2, and this is equation 3. So now we have three equations. Similarly, from just now, we can solve all these three equations to get alpha 0 what value, alpha 1 is what value, and alpha 2 is what value. So we need to solve three equations. But to solve the three equations, all these three equations is complicated. Okay, maybe we have another way we need to discuss later. So I just show you the procedure. So we need to develop all these three equations first, and then the next step is we need to solve this equation to find alpha 0, alpha 1, and alpha 2. Okay, once we found alpha 0 and alpha 1 and alpha 2, we need to replace or substitute back to this equation. Okay, we need to substitute back to this equation, similar as just now for two noded element, now three noded element. So once we found alpha 0, alpha 1, and alpha 2, we need to substitute to this. So we need to substitute here alpha 0, alpha 1, x, and alpha 2. After we substitute to this term, alpha 0 and alpha 1x plus this, so next step as just now. Okay, as just now, after we substitute back, we need to factor. Okay, we need to factor so that we need to factor so that we can form ux is equal to after we substitute back, we need to resolve extend, and then we need to factor the term ui. Okay, ui is a nodal displacement here, plus this term multiplied to uj. So uj is here, or u at xj, plus u plus one more, we need one term multiplied to uk. So uk is nodal displacement at k. Yeah. Okay. So this term, we call n I is a function of x, and this is n j is a function of x. So, and then this is n k. This is also a function of x. So we can find ni, nj, and nk. This is shape function. The same how we can find for two nodal element. So this I just show the procedure how to find ux in terms of shape function. Okay, so as conclusion, we need this first. Okay, so we need this first. This is polynomial. In finite element, we must predict ux based on polynomial. We have three nodes here. So we introduce the boundary condition usi just now. So this is ui equal to this, and then second equation uxk. So this is uk. Uxj come first. So this is uj. We form this equation. All term here is sj just now. This is usk. Yeah, usk is uk. Okay, uk, and comes from this term. So after we introduce the three equations, we need to solve to find alpha 0, alpha 1, and alpha 2. Once we found alpha 0, alpha 1, and alpha 2, we substitute back to ux equal to alpha 0, alpha 1 equal to this. We substitute to here, and this term we substitute to here. And then after that, we solve, or we expand this equation, or simplify this equation, and comes to this. Okay, so now ux is ni ui plus nj uj plus nk uk. So from here we can find what is nai, nj, and nk. So this is important. Ni, nj, and nk represent the shape function. For a node element, Lagrange polynomial interpolation function Lm can be used for calculating the shape function at m node. So this is Lm. This is we call Lagrange polynomial interpolation function. This is Nm. This is structural symbol. We use N just now, but this is mathematical symbol. So this is L. M refer to node, so this is the formula. The formula is pi. Here we have pi. So pi is, if you remember, this is sigma refer to summation, sum, but pi referred to multiplication. Okay. So pi is multiplied here. X referred to X position just now, minus XP. P is start from 1. So this is index, and index from 1 to n. N refer to number of node, the total number of node. So this formula is like this: X minus XP. P will vary from 1 to n, divided by Sm. M refer to node, and minus XP. So P is an index. Okay. From just now, we derive U of X just now. Ux is equal to Ui and I, function of X, Ui of X, this I is referred to node, plus Nj of X multiplied to Uj, displacement or nodal displacement at node J of X. We can replace by N1, I with 1, so N1 U1 plus Nj, J we replace to 2, N2 U2. So this we can find, we can find N1 and N2 just now. We can find using Lagrange polynomial integration function. So we can find by using this. Okay. So generally, N M is this. We use X minus, this is X minus, P is an index, so X1 begin with 1, so P is start with 1, but we have a condition, P must not equal to M. Okay, so X minus X1, this is XM. This is M referred to node. We have, for example, this is node 1 and this is node 2. Okay, either we consider node 1 or node 2. This is M. So minus X1. So then pi we use multiply here. If this is sigma, so we use this is plus, but if pi, so this is replaced by multiplication, multiplied. So this is X minus X. Okay, XP just now is P start with 1, so the next index is 2. So P become 2, so this is index 2 now. So my per sm not minus x2, p is 2, so multiply. Okay, so x minus x, now p become 3, 1, 2, 3, so this is 3 xm minus x3. So this is multiplied continuously, continuously. So this is shown here. Okay, so this is shown here. So this is first. Okay, so comes from this and this second term here. So we have this term and this is third term. So multiply continuously until p, p reach n. So x minus x n, or p equal to n here, and this is sm referred to naught minus xn. So np become n at the end process. Okay, so this is the formula I explained to you or describe to you how to use this formula. Okay, let's consider example for two noded or two nodes element with n equal to 2. So we have this is element just now. This is node I just now we replace with node 1. So this is node 2 or n2. Okay, so we have two nodes here. Okay, this is two nodes element. So n is equal to 2. N equal to 2. N equal to 2. So now we use this formula to find n1 and n2. This is u1, the displacement u1, and this is displacement u2. So after this place take place, it become like this. Okay, so this is original, and this is deformed shape. And this is x1, position is x1 here. At node 2, position is x2. So here, this is position is x. So this also displace. Okay, displace with u function of x. Okay, from just now, ux, we can use a polynomial to approximate ux, and ux for two node element is n1 x of x, u1 is a nodal displacement, plus n2 of x multiplied u2. So this is nodal displacement at node 2. Okay, so we are going to find what is n1 here and what is the formula for n2 by using Lagrange polynomial interpolation function. So we use this formula. Okay, so n1 Okay, and one where m equal to 1 equal to, okay, so refer back to this. So x minus xp, p begin with 1. So this is x minus x1, okay, x minus x1 here, and divide by xm. M refer to naught, so m refer to 1. Okay, refer to 1 minus xp. P is index, index 1 from 1 just now. So we get this term. Okay, now P become 2. Okay, so then this is pi, so this is multiplied. Okay, multiplied. Second term, yeah. X minus, now P become 2. Okay, x minus x2 per xm. So this is referred to not 1. Okay, still x1 minus x2, minus p equal to 2. Okay, so we get the second term here. P will end until n. Where n here is 2. So n is 2. So when p equal to n or p equal to 2, so this will stop. Okay, but we have a condition, p must not equal to m. Here, this is m, this is p. So m equal to 1, p equal to 1. This is, we need to cancel this because we need to satisfy the condition p must not equal to m only. So this is p equal to 1, m equal to 1, p equal to 2. So this satisfies p not equal to m, but when p equal to m, we need to ignore this term. We need to ignore this term. And this is, we simplify, is equal to x minus x2 per x1 minus x2. Okay, we just modify this. So this is minus, we just change the position, x2 minus x. We put the minus here. So similarly at the bottom, so we put minus, so this is change position. So become x2 minus x1, and then we cancel this, we get this. Okay, so we get this. So this is x, n1 is x2 minus x per x2 minus x1. So now we proceed to n2. Okay, so n2 is here. This is n2. So n2 is equal, we start again. So x, we use this formula again, x minus xp, so x minus x1 per m is now 2, m is 2, so s2 minus s1. So this is first term when p equal to 1 here, and multiplied because of pi, so this is multiplied. So now x minus p become 2 now, so s minus s2 per xm, m is equal to 2, so minus p increase to 2 from 1 just now, so s2 now. This condition not satisfy, p must not equal to m. So when 2 p equal m equal to 2 and p equal to 2, we need to cancel. We need to cancel this term. So we just have x minus x1, and this is the bottom x2 minus x1. So this condition we need to consider because m not equal to p. Okay, so finally we found the formula for n1 and n2. So if we consider back to what we derived just now for two not element. Okay, so this is we derived just now. We got an I and nj formula just now. Okay, if we compare to this, okay, if we compare to this, so this is just now we found ni or n1 just now is this. This is x j minus x per xj minus xi. So j we change to 2. So minus x. So xj, j we replace 2. So minus xi, this is x1. So we found that n1 is the same as ni just now. Okay, so from here, n2 we found this. Okay, if we compare to nj just now, so this is x minus xi. So here x minus x1 or I replace to 1. So here at bottom here, so this is xj, this is x2 minus xi replaced with 1 x1 minus x1. So this is also same this. Okay. So this is the Lagrange polynomial interpolation function can help us to find n1 and n2 or the shape function. So the shape function can be found by using Lagrange polynomial interpolation function. Okay, so we go to next slide. This is 3 not element. Okay, so this is, I need to take a screenshot here. The Lagrange polynomial interpolation function. Okay, so this is 3 not element. We have 3 not. Okay, 3 not element. Not 1, not 2, and not 3. Here at not 1 position is x equal to x1, x equal to x2 at not 2, x equal to x3 for not 3. So this is going to replace u1 here, and this is u2, and this is u2, and this is u3. And this is x. Okay, x will displace u function of x. So u x function of x. So we need to predict by using polynomial just now. Okay, we have a procedure to find this alpha 0, alpha 1, and alpha 2 as I explained just now. And finally, we get this. We get ux is equal to n1, the shape function u1 plus n2 u2 plus n3 u3. Okay, so we can use again the Lagrange polynomial interpolation function to find n1, n2, and n3. Okay, so let's consider how to find n1 here. Okay, n1 is, we use this formula, so x minus s1, so x minus s1, so now p equal to 1, m is 1, so s1 minus s1, so s1 minus s1, but this condition is where p equal to m, so this is m equal to 1, p equal to 1, so this is not satisfy this, must or should be p must not equal to m, so if p equal to m, so we cancel this term. Okay, next multiply to x minus x2 now, so the index increase to 2, so x minus x2 per xm, m refer to 1, so x1 minus x2. Okay, so we need to multiply more until p reach n or 3, so n is 3 here. Okay, n is 3 or n is 3. Okay, so multiply to x minus x3. So p become 3 per sm. Sm is s1. So s1 minus x3. So here we can cancel this term. We just take the remaining term. So we found this. So this is n1, and similarly for n2, we use this again. So x minus x1 per x2 minus x1. So m equal to 2 here. Okay, so multiply to this term. So x minus x2 per xm. M is 2, so x2 minus p is 2. So this is, we need to cancel because m equal to p. Okay, m equal to p, so we need to cancel this term. And finally, x minus p change to 3 now, so x minus x3 per x2, so refer to 2, m2, so x2 minus x3, p is 3 now. So we just cancel this term, we only take this term and this term, so this will become this. Okay, similarly for n3. Okay, finally we found n1. So n1 and n2 represent the shape function where ux we can find from n1 u1 plus n2 u2 plus n3 u3. Okay, so n1 and n2 and 3 we can find from here using the Lagrange polynomial interpolation function. Let's go back to here. Okay, let's go back to here. So we found this formula. We can consider for the example now. Okay, for example, we back to two knob element. Let's consider if we have one bar with two nodes. For example, here we have x equal to xi just now, or x equal to x1. Okay, so let's consider if x1 equal to 1 m. Okay, if we put the number here, so this is not 1 and this is not 2. So x2 here is also, this is, for example, this is 4 mm. So L is 3. L length is 3 mm. I use a meter. So x1 is 1 meter and x2 is 4 meter. So L is 3 meter. Let's consider if this is displaced of 1 mm and the node 2 is displaced of amount 2 mm. So the bar now is stretching. Is stretching. The bar now is stretching. So this is final shape. So this is stretching of 1 mm. 2 minus 1. So this is stretching 1 mm. Okay, we want to find what is the displacement here. So the displacement here is we want to find at x equal to 2.5. Oh, sorry. Yes, 2.5 mm. So this is at middle or mid length. So this is 2.5 meter. Here, this is the length 3 meter. So this is 1.5. So 1.5 plus 1 is 2.5. So the position here is at mid length here is 2.5 meter. So we are going to find what is the displacement here. So this is go to new position here. So we can use this interpolation function just now. So ux is equal to, okay, I write it here. So ux is n1 u1 plus n2 u2. So this is equal to, okay, so we consider back the n1. Okay, the n1 we take this formula. Okay, this formula, this is n1. So x2 is 4. x2 is 4. Okay, minus x. X is 2.5. Okay, minus 2.5 per length. So S2 minus S1 represent the length. So this is 4 minus 1. So this is 3. Okay, and multiply to U1. We assume that U1 just now is 1 mm. Okay, 1 mm. So plus. Okay, plus The second term, this is n2, so n2 is x minus x1. X minus x1 is 1. Okay, x minus x1. X is 2.5. Okay, 2.5. 2.5 minus x1. So x1 is equal to 1 per x2 minus x1 is 3. 4 minus 1 is 3. Multiply 2 u2. So u2 here is, we assume 2 just now. Okay, so we found this is u x equal to 2.5 equal to, so 4 minus 2.5 is 1.5. 1.5 per 3 is 0.5. So 0.5 times 1, we get this is 0.5 mm. Okay, so this is comes from this term. And the second term now, 2.5 minus 1, this is 1.5. 1.5 per 3 is 0.5. So 0.5 times 2 is 1. Okay, so 1 mm. So finally we get 1.5 mm. Okay, so if we know from this, if we know the displacement here is 1 mm and the displacement here is 2 mm at node 2, second node. So at x equal to 2.5 meter, the displacement here is 1.5. So this is 1.5 mm. So this is useful or benefit using the Lagrange polynomial interpolation function. If we know the displacement u here, u1 here and u2 here, we can find the displacement at any position on bar element by using here this formula, where n1 and n2 we can directly found from Lagrange polynomial interpolation function. Okay, so I think that's it. This video. See you back in the next finite element video. So see you and bye bye.